Okay, so today we have Alicia joining us, who is a PhD student in Oxford with Michael Bronstein, and she's going to be telling us about guiding diffusion models for macrocycle generation. So go ahead.
Thank you. So, yeah, thank you for having me here. I'll be talking about MacroGuide, which is our paper accepted to ICML about how to use topological guidance to generate cyclic molecules. And it's been developed in collaboration with people from Oxford, Aetherian, Vienna, Paris, and Vienna again. And um, so Well, I guess I don't have to say that AI is being used to help to solve problems in drug discovery, especially how to propose better new molecules. But the focus of the today's talk will be macrocycles and just briefly why we're interested in them. So macrocycles in the definition here are basically any molecules with a ring that has at least 12 heavy atoms, like this one in here. We don't care about the small rings. And just to mention, it's not just cyclic peptides. Sometimes you can see macrocycles being, like cyclic peptides being called macrocycles, but here they just form a subset of our definition of macrocycles. And the reason for why we care about them is that they are really nice drug candidates, and it all comes to this ring. Basically, if you have a bigger molecule, you can have more interactions, so you expect it to be binding slightly better. But at some point, if it gets too big, it becomes too flexible and you lose, for instance, selectivity. So this ring forces the molecule to be somewhat rigid. So you don't really lose the selectivity there. And on top of that, you don't have the like big penalty when you bind a new target, the entropic penalty because it's rigid. So you have better binding affinity. So like a linear molecule would be having like too much freedom in solution, and then like the binding penalty would be huge, and you don't have this problem with macrocycles. And this is like one of many drugs that are macrocycles. So why is it hard? So, well, here we're just trying to show the first model to generate arbitrary macrocycles, and the reason for why we think it's been such a big problem so far is that there is really not that much data available if you want to train a model. We're talking about 40,000 macrocycles compared to many, many millions of small molecules. And the way the usual diffusion models work, they assess often on some local properties like validity or angles, or they're just trying to approximate the training data, or like the noisy versions of targets. But they have no global really notion of topology, in this case a ring, so they are just not performing well. And just a brief recap of what diffusion models are compared to, say, flow matching models or other models, is that we basically just want to draw samples from our distribution of molecules, and we corrupt the samples first. We just add noise progressively to them until we have um, no data structure left in there. And then we can reverse it. We learn the score, and then well, once when you have the score, we can regress it and to train against it to get our loss, to get our conditional score. The network is usually parameterized by, say, graph neural networks or whatever works for molecules. And then we just reverse this by like iteratively getting the molecule back from noise. This is, say, in comparison to flow matching models where we usually skip the score and we get the like velocity field directly and we try to learn it. So there are different models there, but the one that I'll be talking mostly about will be the diffusion models. And yeah, how this looks like in practice in molecules, you just get your point cloud, usually with a fixed number of atoms, and the atoms can change identities. They can move around, and you can have bonds that can be either later, like here, or often they are modeled at the same time as everything. And features can be like discrete, categorical. There is like a lot of different architectural choices here to be made. But usually we just start with the data, we noise it progressively, and then we learn to recover this trajectory back by learning the score. So that's the molecule generation part. And to talk about how we want to generate macrocycles, we'll have to go to a rather well-established branch of mathematics, which is topological data analysis and persistent homology. And basically, I'll give you a quick introduction to what you probably need to know from there if you want to understand this method. So it's a big field, and this is a really small subset of it. But what we'll be using is that for every like molecule you see, you have this arrangement of of atoms, the point cloud. In our case, it's in 3D. Here is in 2D. And topological data analysis allows us to extract the information about the structure of the point cloud, and it can do this in a differentiable way. So to begin with, I have the atom positions, as I said, in 3D. And then I have a notion of scale, in which, in this context, the scale is just radius around the points. So you can imagine that every atom here has a ball growing around it. And as the scale increases or the radius increases, the balls keep on merging into each other. And at some point, everything becomes one big blob. And there are different features here. So the most intuitive one is the H0 components. So this is the clusters of atoms. So we start with the same number of H0 components as we have points. And then like as the radius grows, we end up with only one cluster of atoms with only one H0 component. So what happened here during this so-called filtration is that some features were born, all of them were born here at 0, and they died at some point. The death happens when two components merge into each other. So basically, yeah, at some point when these two connected, one of them died. And then as the thing progresses, we are left with only one component. And this component here has technically infinite death, but we don't really care about it. And then the more interesting part is the H1 components. So these are the features that are rings for us. So basically the ring is kind of born when the longest bond in it gets closed. So at some point here you can see this ring was born. So the birth of this H1 component happened at some scale between 0.3 and 0.5. And as the scale increases, the ring will at some point die. The death is slightly less intuitive and depends more on the like filtration you use. But let's say it's mostly related to the kind of length of the like narrowest constriction of the cycle, more or less. And we record when things are born and when they die, and you can see that there's a ring here that was born later, and then it died later at some point between 1.5 and 3 here. So we basically extract all of this information, and we'll have the information about which atoms corresponded to birth and which ones contributed to death events, and we will use this information. And just to mention, you can extend it further to like H2, H3, etc. And H2 would be just voids in molecules. If you wanted to deal with something that has like, say, maybe cages, then these H2 could be useful, but we didn't do this here. So yeah, and by the way, if you have any questions, you can ask me anytime. I don't think I can see the chat, but I can definitely see the hands up. So now the question is like, how do we use this in practice to add this to our diffusion models? And there are many choices you can try to put in here, but we chose to use guidance. So basically, it's just we take a pre-trained model, and then as you generate it, it would usually just go step by step, removing noise and generating the molecule using this score, the learn score. But we, on top of that, add our guidance. So you can kind of visualize it as just basically at every step or every few steps of denoising, you can add this additional force strength to push your point cloud into being a macrocycle. So just to reiterate, it is training free because you can just apply it to an existing model. Like we really don't retrain it. We just take the existing checkpoint, we generate molecules, but we force them to be cyclic. We show that it's lightweight. It's really quite quick. You don't give, it doesn't put a lot of computational overhead. It's flexible, meaning that you can just choose the ring size you want. Like you don't have to say train with labels like this was the ring size that, or you don't have to just hope that your ring size will be what you want. You can just be like, I want the ring size to be more or less that. So that's nice. And it's quite general because it's disconnected from the architecture. So you can just take the model you like and then add it there, and it may work well out of the box. And we tested that with a few diffusion models, a flow matching model, and other things. So, well, depends often on the performance of the base model, but it seems to be working well and to be transferable between different things. So, how this looks like. So, basically, we'll be trying to start from the noisy structure, the noisy point cloud. And instead of forcing the molecule to take its usual denoising path to go to some kind of point in the training data, we will try to add this topological guidance. So worth noticing is that this topological guidance basically works only when we are outside of our definition of what a cyclic structure is. The value of it will be equal to 0 if our structure is already macrocyclic enough. So we'll be just only pushing it whenever it leaves our definition of a cyclic structure. And we hope to reach this density of macrocycles, which would be usually quite hard to obtain by just using the original data distribution. And just to show you what we'll be dealing with, these are some examples of the generated macrocycles. So when I'll be talking about unconditional case, I mean just this top row. So we just generate things in vacuum. And when I'll be talking about conditional case, I mean the protein pocket. So here on the left is an example of a protein pocket with a macrocycle in it. And on the right-hand side, we have a slightly different case. There will be a bicyclic molecule. So here I just wanted to have two components instead of one, two big cycles, but I'll talk about it more later. But just to mention, yeah, we'll be trying to get the molecules with a big ring like that. And we don't care about the small rings, they're fine, but they don't affect our definition. So how do we do that? So I'll talk about the F values in a second. They're like scalars here, but just to show where the actual directions and the guidance comes in. So we'll have three different functions trying to guide the molecule towards being a macrocycle. The first one will be the cycle size. It will be the H1 depth function. This function is related to the depth of the largest H1 component. So just as a recap, the largest H1 component will be the structure that is the largest out there and looks like a ring. And we'll be just trying to optimize its size. And like when you do this filtration, you'll get this differentiable information about which atoms contributed to the depth of the cycle. the depth will be like the collapse when you grow the balls that are big enough to touch. It will be say these two, and then we'll have the information that these two should be pushed in the opposite directions to make this thing grow. Similarly, we have the H1 birth to control when the cycle is born, because the important thing is that the like TDA notion of a cycle is not exactly the same as our chemical notion of a cycle. Like TDA can see a big point cloud and be like, oh, it's a cycle. But if the points are too spread too far apart, there won't be an actual chemical bond in there. So we want to keep the points close enough to have some notion of chemical bond in there. Just to mention, these bonds here are only added to make it a bit more obvious what is the chemical scale here, but the actual bond information is not passed into the TDA model. It only uses the point cloud as the information. So yeah, these two just try to optimize the cycle. And on top of that, we add the H0 component, which is not that strictly necessary. It's more to prevent the molecule from being disconnected. So how it works is that unlike here, you can have many functions here. And basically, as the points grow, at some point, everything will merge into one H0 component. But if you have a cluster of points that is on average, not on average, but like is kind of disconnected from the rest, the depth of this will be higher than our threshold, which in our chemical information, it will mean it's disconnected chemically. So we'll try to penalize it for that, for the H0 depth to be lower than the threshold we choose. And I'll explain in a second why there's only one arrow here. Technically, from TDA point of view, the arrow would be on both sides, but we make it in such a way that there is only one direction for it to move into. And what are the actual values? So the H1 depth, the one that controls how big the cycle is, we choose it, we put it a range of values we want to keep it in. So we specify the like minimum size and the maximum size of it. And then we just optimize it to be in there. Like if it's already there, then there is no gradient here. It will be equal to 0. But whenever it's outside of this range, because it's too small or too big, it will be pushed back into the desired size. Connectivity is basically we just want to keep it closed. So we choose this value here of what is our bond length. We chose it in the end to be 2 angstroms. So this is more than the usual bond lengths you expect to see in organic chemistry. But we wanted to give them all a bit more room to play with things. But we want to optimize this to be below the length. And then the molecule connectivity, you find again all the disconnected components. It's not just one. And we again want to force it to be below the same threshold of 2 angstroms. And what I mentioned about the gradient of H0 being only on one atom, as opposed to being on two, is because we observe, and it's somewhat intuitive, that if you don't mask the gradients, if you propagate it on both, basically you'll be in a situation where you have this nice ring and something disconnected, and instead of just bring it closer in a somewhat intuitive way, it will move everything closer to each other and the molecule will become just too linear. You may then lose all of your H1 components and get linear boring molecules. So we just mask it to find the one that's closer to the centroid. Let me just move this. And yeah, so we find the one that the cluster that's close to the centroid, and we only propagate the gradients to the other side. And we bring it closer. So in practice, what you should be aware of is that when I'm talking about all of these gradients are really, really sparse. So for a specific snapshot that we see, Um, the gradients are only on a few atoms. So for like H1 death, it will be like 2 atoms. H1 birth will be again 2 atoms. And this one can be, um, and like these will be 2 atoms, and a few atoms. So you could be arguing that there is not enough gradient there to actually really move the points in space, especially compared to denoiser, because like at every step, the denoiser, the base model, will be able to move every single point, and the topological guidance will move only a subset of points. But in practice, that is really not a problem. So the features converge really quickly. So say 50 steps and you get what you want. And then for the rest of the diffusion generation, the point cloud stays in the like cyclic shape we want, and the denoiser is just trying to optimize it to be closer to a valid molecule. So just to briefly explain what we see here, the H1 death was the one that was controlling the cycle size. So it quickly reaches this region that we specified as our desired cycle size range. And if it's in this region, it receives 0 gradient. So it's just like moving here without gradient, or being pushed back quickly if it's outside of the range. And similarly, the cycle closure and the connectivity get really quickly pushed below the chosen threshold of 2 angstroms. And they stay there for most of the generation. And the cool part is that they go down towards like real bond values only at the very end. And this change here, like again below this line, there is no gradient whatsoever. So this change is only driven by the denoiser. And the denoiser probably just realizes that the molecules are too close to not be connected, but too far to be actually connected. So it kind of brings them closer together to have the say 1.6 or similar angstroms, and have an actual chemical bond there. So it just like kind of fixes the kind of things that topological guidance on its own wouldn't really see. And yeah, and the results. So in the unconditional case, the base model that we use here, which is Moldiv, can sometimes produce macrocycles. But if we apply topological guidance to it, we can really push it quite far. And the interesting thing is that it also pushes the pose-busters performance. So this is the like suite of metrics to see if the generated pose is good. And the reason for why this is, we believe, is just because we give more time for the denoiser to actually try to fix the bonds, because we fix the cyclic structure quite early on in the generation process. And similarly here, we use a different model that can handle conditional generation, and we push it from like even less to also very high performance, almost 100%, with also an increasing pose-busters, probably for similar reasons. And we check a few other ways to see what else can generate macrocycles. So just to mention again, to the best of our knowledge, there weren't any methods to generate arbitrary macrocycles. So we put a few baselines. We tried to do fine tuning. We took all the data we have in this macrocycle DB data set, which is not a lot, and we just took the model and conditioned to do further fine tuning with this data set. And we see quite nice performance in the unconditional case, but sadly it doesn't work in conditional at all. And probably the reason is that it just doesn't have enough force to keep the cycle open enough. Like it did produce slightly bigger cycles than unconditional, like the unfine-tuned model, but often they were like say size 9, 10, maybe 11, so they would like miss the definition of a cycle just because they didn't have enough force to not be closed by the protein pocket, which is quite narrow space sometimes. And so yeah, this was the best performing honor based model, but that was like, yeah, very short of 99 point something performance. And we tried a few other simpler things to see if TDA is really needed. The naive version is basically you just choose, say, 12, 14 atoms out of your point cloud, and you just arbitrarily say, oh, these are like that, this is going to be the ring between them, and then like um, you push the opposite atoms apart, and like, I don't know, say one, and would it be seven or something? And then like the neighbor is close, so like one close to two, two close to three, etc. So like a very naive version of guidance. And it does something in the unconditional case, but doesn't really work in the conditional case. And yeah, other things, we just try to see what happens if you just add different noise instead of starting with Gaussian and you start something that really looks like a macrocycle, and it didn't help at all. So yeah, we think that MacroGuide is quite a nice method compared to others. And just to mention how you can control other important parameters. So TDA doesn't really have a notion of what is the cycle size in the like chemical meaning of it. It only sees the point cloud, but the the cycle in the point cloud can be really squeezed in one direction, and it's the narrower direction that defines the depth of the component. So um, you could try to develop some theoretical models to try to predict what the size would be. And we did some simple models using some trigonometry, just kind of build like a kind of flower shaped cycle and calculate the death time of that for different bond lengths, say bond length 1.5 or bond length being 1. And this can give you some estimate of how this should scale. But in practice, because we know that this thing can always get bigger if the cycle is slightly squeezed, in practice, the best way is to just see how it performs. And basically, you can just specify, oh, I would like this to be in this range. And then like you have say, a way of controlling, oh, it will be around 15 atoms big, the cycle. But um, you don't really get a control over how many atoms exactly, which in fact is probably a good thing because you just specify how you'd like it to fit in the pocket rather than being too restrictive about the size. But this is something to keep in mind. And then a few other things we tried to see. So basically, another approach that people use in chemistry to move beyond macrocycles is to use bicyclic molecules. The reason why they do this is because if you move towards even bigger molecules, at some point your ring becomes too large that you lose the nice properties of macrocycles. So then the solution is just to add another big cycle and you still have then nice selectivity, binding affinity, etc. And you can do this here very easily. Instead of just optimizing one H1 component at the same time, you just optimize two of them and it will produce a structure with two cycles and it performs well in both unconditional and conditional cases. Then a few other things. So the H0 we mentioned, so this is the one that controls if the molecule is connected, is quite useful, especially if you want to generate big molecules. So the experiments we've shown before were for 30 atoms. So that's like not shown here, but that would be see here. But as you increase the size of them, they're more likely to be disconnected, especially because a lot of the molecules in the training data set are quite small and the models are not really used to dealing with such big things. And we see that we can then use just H0 guidance to keep it connected for much longer. it does decrease at some point too, but you can go to even as big as 100 atoms and still be well connected before it gets destroyed. So yeah, the like topological guidance can be used to more than just generate macrocycles. Like if there is any kind of point cloud feature that you'd like to optimize, you can try topological guidance. And then just to mention at the end, it is quite fast. So basically, here we just have the base MoSnapper protein conditioning generation, and we show that like the extra overhead from adding the topological guidance is really quite small, especially if you think about what is the increase in macrocyclic generation. So for this protein conditioning, we were at less than 1% and we go to almost 100%. So that's 100, 300 times increase in the generation performance for really quite small cost. But if you think that this is too much, we also check what happens if you don't apply it at every step, but every few steps. So like instead of 1,000 denoising steps, you do that every, say, 5 steps. Like the denoiser still works at every step, but the this thing gets divided by 5 because it gets just like applied less often. And performance-wise, it is still okay. You can lose, say, a few percent, 10% of macrocyclic generation, improve a bit on other metrics sometimes. But yeah, if you think that the cost is prohibitive, then you can just try applying it less often and it may still work very well. So yeah, I just think that's it. And if you have any questions, I'm happy to answer and thank you.
Yeah, thank you very much, Alicia.
Thank
Are
you.
there any questions in the audience to start with? If not, I can.
I yeah
Yeah, oh yeah, you go ahead, Ricardo.
yeah I can go ahead. Yeah, I have a few questions. Um, One of them is like because in molecular generation with small molecules, we've seen that flow matching works really well. So I was very curious if you experimented with it or you applied diffusion just because you had that model as baseline.
Um, so we got asked the same question by a reviewer, and we did apply it to flow matching. We applied it to FlowR, root, maybe one of these models. And it did perform well too. As in, like, it did push the performance to 90 or something percent generation. So, as in, like, it is probably expected that flow matching will work slightly worse if you apply guidance just out of the box because basically you don't really have the score which tells you how far you're off your distribution. You only have like the velocity field, and if you mess up with it, it I don't think it has like that nice properties to like go back. So it's slightly expected to be slightly worse, but like it still worked well. Like you got more than 90% macrocycle generation.
90% compared to uh,
Oh, I will need to check.
with the conditional
25.
one.
That was conditional one.
All right.
Like a few percent or 10%. I would need to double check. But
Yeah. And then I'm very curious about another aspect because, all right, I'm not a chemist, but did you already do some tests on synthetic accessibility of the microcycles generated?
um no, and I think it would be very cool to check. As in like just to mention that like just applying say metrics like SA out of the box is probably a bad thing to do for macrocycles because it has really no notion of how bad the macrocycle is or how good. It only, from what I remember from the formula it uses, it as like +2 if something's a macrocycle. Um, doesn't give you like a nice understanding of how some macrocycles are better than others. And Well, for macrocycles, the most important bit would be probably turning the linear thing into the cyclic thing, and it's a really complicated thing from chemistry point of view. And yeah, I know some other people work on that, and that would be like a very good thing to check, but that would be more for a chemist, I believe, to develop better metrics to check like which macrocycles are good. Because like from like if you say want to obtain the like say energy of this ring, it is not as easy as like putting into postbusters, which gives you only the energy of the like how strained something is. You'd have to do this, I think it's called a homodesmotic reaction to like break the cycle, but in a very specific way, and you have to choose how you do this. So yeah, it's like a very important problem and but also a very complicated one. So I think I would like to
Yeah.
check it at some point in the future, but yeah.
Yeah. And then I just wanted to ask if you can argument a bit more on the torus noise schedule. At some point you mention it in the slides.
Which noise schedule?
If you go back in the slides, I think at some point you yeah, in the next one.
Wait, they're like back or future?
No. Go forward. Uh, here, yeah,
Here.
yeah, here. Torus
Mhm.
noise.
Yeah, what was the question?
What is this torus noise?
This was like
How does it?
basically a toy way of starting it. So just like basically like theoretically if you learned a Gaussian, like if you made your molecule always go to Gaussian, you should start with Gaussian to sample from it. In practice, we can start sampling from a lot of different things, and it was just checking what happens if your noise instead of being like a Gaussian looks more like a kind of torus
Oh, all
shape
right. Yeah,
thingy.
I see. Yeah, thanks.
And can I maybe just double check a few kind of details about the models that you were using? So are you just sort of applying the guidance just to the coordinates and then letting like atoms and bonds kind of sort themselves out according to the default vector field, or do you do like bond inference at the end of the generation or something like this?
Um, I guess this depends on the base model you choose, but in these cases, the base models were both modeling bonds. So, like at every step, the denoiser was dealing with all the information it would usually deal with. So there would be like coordinates, atom types, bonds, maybe something else. But the TDA thing would only see a subset of this information, which would be only the coordinates. So the TDA would only change one bit of the kind of um, point cloud you see. But yeah.
So you're kind of like you're able to just guide or push the guidance on the coordinates, and then the graph kind of follows along from what the coordinates turn out to be.
Um, as in kind of, as in like the graph is like as in like just a adjacency matrix saying what's the probability of there being bonds and like if you move it if you move everything basically with the TDA, like all the coordinates, then the denoiser at next step will try to fix it. So it is kind of a constant battle between TDA and the denoiser in some aspects, but in practice they usually manage to work well with each other, and the denoiser manages to fix all the like TDA mistakes that can be introduced.
And did you find that the TDA had to be applied like kind of throughout the entire vector field? Or I think you had one slide, maybe a couple of slides back, where it looked like you only really needed it at the very start, and then the rest of it you could just sort of leave. Once you'd found like roughly the right part of the density, you could just let the, unguided generator do its thing.
So there's like I guess three things. Like there wasn't as in like that was mostly usually score rather than the vector field, just to be precise, but like I guess doesn't much for much. Second, you could apply it every few steps. Like that's how I mentioned, you could try to make it run faster, but like to answer in the best way. Basically here, the reason for why I show the errors only sometimes, it's basically this information here is actually taken kind of from here, because in practice we see that um, you are okay with applying the TDA guidance only at the beginning, and then it's only there to make sure we don't go back from there. I believe if you were to stop your TDA guidance, it could probably go back outside of the your definition of a cyclic structure. But the important thing here is that like if your green thing is in this region and if these two are below the threshold of 2, the TDA guidance will exist, but it's literally equal to 0. Like it doesn't change anything. So basically that's what is shown here. Like well, the reason for why it's not here is just because it's equal to 0 if it's within our definition of a cyclic structure.
So it's even just within the first sort of 100 steps out of 1,000 or so, you really need to push it to the right place, but then the rest of it is just like keeping it in the place that it gets to.
Kind of, yeah. As in, like, we've been also playing with applying it late instead of applying it every now and then. And then, well, the later you start, the like slightly lower the chances of you getting it right. But like, you can actually start quite late on, like, say here and here, and you still get a decent performance. It's just, but then you lose in other metrics, like well, basically like the pose and everything. So the reason for why we choose to start early on is that it gives like the most time to the denoiser to actually make it look nice, as opposed to like getting the almost nice molecule, kind of, because like at this stage here the molecule would kind of look almost like a molecule already. So if you apply the guidance at this stage, you'll break a lot of things and the denoiser really won't have enough time to fix everything, at least in this like simple thing that can only move forward. Yeah, I guess there are some models that just kind of try to go back in time if they see the structure is too noisy. But yeah, this one is rather simple.
Cool. Yeah, thanks. I just like one last maybe slightly provocative question, if you've considered it or tried any experiments on this, is I guess this kind of relies on like the unconditional model on its own is already able to generate macrocycles. Like there are some macrocycles in its training distribution. So this guidance mechanism kind of relies on the data distribution that the model is modeling contains macrocyclic data, and you're just sort of guiding it towards that area of space. I wonder if you like thought about or tried, like if you were to remove that, those macrocycles from the original training data, do you think would the model still have a chance of being able to, like, having never seen these kinds of structures before, would it still be able to push things towards the right area?
I think so. As in like well, we didn't want to retrain just in case. Like it's a bit hard to argue that we retrain the correct way, like just by removing. But just to mention like the amount of macrocycles in the training data is less than 0.5%. I don't remember the exact value. And we did some comparison later on of the say kind of like microcyclic distribution, like whether it hits the same distribution as your training data or if it's like different. And I would say, as in like, it does generate different macrocycles to your training data, and they're like different to your distribution in a way. So, yeah, to be honest, it's a very hard question to answer because it really depends on how you define like similarity between things. And yeah, like basically, yeah, it's as in like I would say this model doesn't really need to have any microcycles in the training data set. Like I'm almost certain you can remove them from the training data set. And not only this, but also the base model will generate macrocycles by chance every now and then. And yeah, But then if you add this guidance, it can modify a lot of things as well. So another point to consider would be that a lot of the macro cycles in the kind of training data, especially if you look at like natural product macro cycles, are huge and they're like have a lot of kind of fused rings or something. And then like if naturally if you force the model to have fewer or more atoms than your training distribution, you can't really hit the same distribution technically. So yeah, as in I would say it can definitely go beyond the data distribution it's seen. But yeah, I don't know.
Yeah, cool. Thanks. No, I think it's really some really interesting results.
Yeah,
So,
I agree.
any final questions? If not, then we'll thank Alicia again. Yeah, thanks for presenting for us, and thanks all for joining. And yeah, hopefully see you at another iteration of this next time.
Yeah.
Thank you.
See you.